timer. And yeah, it's going to be very exciting to hear something about the homology languages of higher dimensional automata.
Let's wait and see. Okay, so thank you, Uli, and thanks to the organizers for the possibility to give this talk. So I'm going to talk about homology of higher dimensional automata. And so we have already seen higher dimensional automata in Uli's talk, in Tracer's talk. So just I can brief about that. So higher dimensional automaton of our alphabet sigma consists of four things: a pre-cubical set, then a particular vertex, the initial state, a set of vertices, the final state. Actually, the initial final states are not important for this talk. What is important is the labeling function which associates with each edge, the label in this alphabet. And this has to be done in such a way that opposite edges of squares have the same weight. As we already know, higher dimensional automata can be used to model concurrent systems. Here we have a picture of higher dimensional automaton representing the state space of the system given by Peterson's mutual exclusion algorithm. So the vertices of a higher dimensional automaton represent the states of a concurrent system. The labeled edges represent the transitions, and I like to see it like that. Squares and higher dimensional cubes represent independence of actions. If we have in some state n actions enabled, and they can be executed in any order, even simultaneously without any relevant difference, then they are considered independent, and this independence is indicated by an n cube starting at that vertex. Okay, so such a higher dimensional automaton can be realized geometrically as a topological space, and therefore it has homology, and it's this homology I'm interested in this talk. So the meaning of the transitions and the paths in a higher dimensional automaton is given by the labeling function. And so in order to better understand the meaning of homology, I would like to introduce a labeling at the level of homology. And with this, I have to define the homology language. Okay. Before I can do that, I have to introduce this notation here for the starting edges of the cube. The edges EI of x. So if x is an element of degree n greater than 0, so not a vertex, then in its origin, this n cube has n edges starting. And these are the edges EI of x. For instance, in this square, we have the origin here. And we have the two starting edges. If it was an n cube, then we would have n edges, E1 to En. I'm sorry, I'm not in the camera. That's okay. Okay. Okay, and so with this, we can now define labeling at the chain level, and then define the homology language of an HDA. So let's take an HDA over an alphabet sigma, and this works over an arbitrary principal ideal domain. Choose. And then we consider the cubical chain complex of the HDA, which in dimension n is generated by the n cubes. And the boundary of n cube, the algebraic boundary, is an alternating sum of its faces. And then we also consider the exterior algebra on the free module generated by this alphabet. And with this, we can then define the labeling chain map from the chain complex to this exterior algebra, which we consider a chain complex with a zero differential. And this chain map is defined on generators, so on n cubes, by this formula here. If n is 0, so the cube is a vertex, then we associate simply the unit of the exterior algebra. And if the dimension is greater than 0, then the cube has these starting edges, and the algebraic label of the cube will be the exterior product of the labels of the starting edges. And this is indeed a chain map, and therefore it induces a morphism in homology. And the image of this morphism in homology is then the homology language of the HDA. Okay, and so the homology language will be a graded submodule of the exterior. The homology language is reasonably compositional. If we have two HDAs, A and B, we can form the tensor product. This has not been defined this morning, so I cannot do it. But geometrically, the tensor product corresponds to the Cartesian product of topological spaces, and formally it's defined in a way similar to the tensor product of chain complexes. From the concurrency point of view, it's also important because it permits to model the parallel composition of independent concurrent systems. And so the homology language of the tensor product will be the exterior product of the homology language. And if we take the coproduct of the two HDAs, the coproduct models the non-deterministic sum of systems, then the homology language of the coproduct will be the sum of the homology language. The homology language is also natural, so compatible with morphisms of HDAs. Actually, morphisms of HDAs are kind of very rigid, or too rigid, actually, because if you think of such a tensor product, A tensor B, there won't exist any morphism from A tensor B to B tensor A. But actually, these tensor products should be isomorphic, because if the tensor product models parallel composition, which is a symmetric operation, then this symmetry should be reflected at the level of the HDAs. And therefore, I propose to use a more flexible notion of morphisms, which are cubical dimaps. Actually, I will only consider simple cubical dimaps, which suggests that there are also more complicated cubical dimaps, and that's the case, but we will only consider here a simple cubical dimap. So a simple cubical dimap from a precubical set P to a precubical set Q is a continuous map between the geometric realization that sends cubes to cubes, n cubes to n cubes, but with the possibility that there is a permutation of the coordinates. And then a simple cubical dimap of HDAs is a simple cubical dimap of the underlying precubical sets that preserves the initial and final states and also labels the edges. And with these simple cubical dimaps, we can identify the tensor products A tensor B. Okay. And for the homology language, we have the following result. So if we have two HDAs, A and B, such that there exists a simple cubical dimap from A to B, then the homology language of A will be contained in the homology language of B. And if the simple cubical dimap is a homotopy equivalence, then actually we will have equality of homology languages. So this can be seen as the result that the homology language is a directed homotopy invariant of HDAs. Actually, the first part of the theorem is maybe more important than the second, because if we see morphisms and maps as simulations, then this result implies that the homology language is invariant under kind of simulation equivalence. For example, if we take an HDA A and let B be the free symmetric HDA generated by A, then there will exist simple cubical dimaps in both directions, from A to B and from B to A. So they can be considered kind of simulation equivalent, and therefore by the previous theorem they will have the same homology language. And these two HDAs are by no means homotopy. Okay, so the squares and higher dimensional cubes in an HDA represent independence of action. So one can expect that the higher dimensional topology of an HDA contains information, global information on independence in an HDA. And this should be reflected in the homology language then. And that's actually the case if we consider this concept of independence. So if we have an HDA A, then we say that HDAs A1 to AN are independent in A if there exists a sub-HDA B of A and the permutation theta such that this sub-HDA is isomorphic to the iterated tensor product of the A theta. And with this notion of independence, one can show from the previous results that if the HDAs A1 to AN are independent in A, then the exterior product of their homology languages will be contained in the homology language. So the independence of the AI is reflected in this way in the homology language of A, and we can look at the homology language of A in order to infer information on independence in A. Okay. So now, having this homology language, one would obviously like to compute it for concrete concurrent systems. And the first problem one encounters here is, given a concurrent system, how do we construct an HDA for that concurrent system? Maybe the most, and this has already been said this morning, the most basic and important, maybe model for concurrency is the one of transition systems. So we can suppose that we have a transition system semantics for the concurrent systems we want to consider, and then the question becomes how to construct an HDA from a transition system. So a transition system is simply a one-dimensional HDA with the particular requirement that an edge is determined by its endpoints in its label. That's not a restrictive condition, right? And here you have a picture of the transition system model for the state space of Peterson's algorithm. This is constructed in a straightforward standard way. And so the question is, how does one construct an HDA from such a transition system? So this question has been addressed by several people in the literature. And although the methods may differ in detail, the overall strategy is always the same. One constructs the HDA by filling in empty squares and higher dimensional cubes. And then the first question to decide is, which cubes do we want to fill in? Which empty cubes do we want to fill in? And one has obviously always the option to fill in every possible empty cube. And sometimes we want to do that. But sometimes maybe we want to have a more refined filling rule. And for example, if we have an asynchronous transition system that comes with an independence relation on the set of labels, so an irreflexive and symmetric relation that indicates independence of actions, then in this case, you would like to fill an empty, say, square, only if the two starting edges would be independent in the sense of that independence relation. Okay, but whatever you choose with respect to this question, which cubes to fill in, you will encounter a technical problem, which is, what does it mean to fill in an empty square? How do you fill in an empty square? To fill in an empty square means to decide which of the two starting edges is the first and which is the second. And so there are two possibilities for that. And you have a choice. And unfortunately, this choice matters. Different choices can lead to HDAs with different properties. And so in this situation, most methods you find in the literature will have the wise solution to fill in an empty square always in both possible ways. The drawback of that is that this leads to very large HDA. And so from a computational point of view, it would be better, or desirable at least, to have a more economic filling construction. And fortunately, it's possible to set up such a more economic filling construction that is consistent with a symmetric approach, where one fills in squares twice. And to make this more precise, let us look at this general construction here. So let's take a transition system and a relation on the set of labels. This can be any relation. So it can be an independence relation, so in particular symmetric, but it can also be an asymmetric relation. It can be simply any relation. And then let's say that an HDA is an HDA model of the transition system with respect to that relation, if these four conditions here are satisfied. So first, the one skeleton of the HDA should be the transition system. In other words, we construct the HDA on top of the transition system. Then if we have a square, then the labels of the starting edges should be related by the given relation in this way. So if the relation is symmetric, then if we fill in an empty square, we will fill in the empty square twice, once for each ordering of the starting edges. And if the relation is asymmetric, then we will fill in the empty square at most once. Okay. So in principle, it's possible to fill an empty cube various times, but this should not be possible without like switching the ordering of the faces. And this is set in the third condition. And then the HDA should be maximal with respect to these conditions, meaning that all say admissible empty cubes are actually filled in. And as I said, variants of this construction have been considered by various people. And then one can show that the HDA model of a transition system with respect to such a relation exists always and is unique up to isomorphism. Okay, and with respect to the homology language, we have the following results. So if we have a transition system and an independence relation on the set of labels, so an irreflexive and symmetric relation, then it's always possible to choose an acyclic relation whose symmetric closure is that independence relation. So an acyclic relation is simply a relation that, considered as a directed graph, has no cycles. And then A of the transition system with respect to the independence relation, and an HDA model B with respect to that acyclic relation, then the theorem says that A is isomorphic to the free symmetric HDA generated by B, and this implies, as we have already seen, that the two HDAs have the same homology language. So from the point of view of the homology language, it doesn't matter whether we construct the HDA using the independence relation, the symmetric approach, which leads to a very large HDA, or if we use a more economic construction using such an acyclic relation, we get the same homology language. To compare the sizes of the two HDAs, since A is the free symmetric HDA generated by B, for each n cube in B, we will have n factorial n cubes in A. So A is really enormous in comparison with B. Okay, so now I would like to show you through an example how you can compute and analyze this homology language using software. We need as an input a description of a shared variable system in the Promela language, which is the process description language of the famous spin model checker. And then we need three pieces of software. First, PG to HDA, which you can find on my web page. This computes first a transition system, and then from this an HDA model of the given concurrent system, using an acyclic relation whose symmetric closure is an independence relation where no two actions of the same process can be independent. It computes also the chain complex of the HDA and the labeling chain. And then we need chomp in order to compute homology. And we need chomp in the original version by Pablo Pilaci. And these programs permit to compute the homology language in such a way that it can be loaded into Sage for analysis. So the example I want to consider is the classical dining philosophers example, which everybody knows. So 5 philosophers have dinner at a round table. In between each 2 neighbors at the table, there's a chopstick, but in order to eat, the philosopher needs 2 chopsticks, which creates a problem because the neighbors at the table have to share a chopstick. And then in order to eat, to have dinner, all philosophers proceed the same way. So first they think, then they wait for the left chopstick. It could be taken by the neighbor. Have to wait, and if it's when it's free, they pick it up. And then they do the same with the right chopstick. Then they eat, and then they release the left, and then the right chopstick, and then they repeat this procedure as many times as you want. So this can be described in Promela like this. So we have an array of 5 integer variables which correspond to the chopsticks. Actually, during the program, they can be only 0 and 1. And so 1 means free, 0 means taken. And then we have the 5 philosophers who execute this loop. Like think, then pick the left chopstick, pick the right chopstick, eat, put the left chopstick down, put the right chopstick down. And the meaning of these actions here is given in these definitions here. So think and eat are simple skip actions, so with no effect on the shared variables. Then, for instance, pick the right chopstick is in an atomic step, check whether the chopstick to the right, so with the same index as the current philosopher, is free, so greater than 0. And when this is the case, take this chopstick by decreasing the variable from 1 to 0. Then pick the left chopstick is the same, but with the index of the left neighbor, which is the current ID plus 4 mod 5. And then put the left chopstick down and put the right chopstick down is to increase these variables again from 0 to 1. Okay. And now we can compute the homology language, mod 2, so with Z2 coefficients, in order to have no problems. Technical, it's not really, but it's implemented like this, so there's no problems with signs in the differential of the chamber. So I'm giving this, using this command, which calls these programs and writes the homology language into a file, which we can, hl.sage, which we can load into Sage. And with load, okay, and then the homology language is in Sage. The exterior algebra here is lambda, and if we want to see the generators, so the elements of the alphabet, we can type lambda.gens. And the elements of the alphabet are the actions of the philosophers, but for each philosopher an individual action. So they come with process IDs. And this looks like this. So there are 30 generators here. Okay. And then the homology language is a graded submodule of the exterior algebra. So if we want to see a basis in degree 1, we can type HL1. And this gives us this 5 generators, which visibly correspond to the 5 philosophers. The homology language in degree 2 is obtained by HL2, and so on. And this gives this, which looks a bit harder to understand. But what does it actually mean to understand the homology language? It simply means to be able to decide what is in it and what is not. And that's easy to decide with a program like Sage, because we can solve matrix equations. So if you take an arbitrary element of degree 2, so a sum of products like this, like arbitrary, think 0 times eat 2 something plus put left 3 times pick right 1, then in order to decide whether this element is in the homology language in Sage, we can simply use solve this matrix equation here. So there's a matrix in each degree. So in degree 2, HL2 matrix, which is a dense matrix. To access this matrix, we can write this. And then we can do solve left V2 of X. So X is an element of the exterior algebra in degree 2. The exterior algebra has a monomial basis in each degree. V2 of X is simply a coordinate vector of X in this monomial basis. HL2 matrix is a matrix whose lines are the coordinate vectors of the basis elements of the homology language in degree 2. So X is in the homology language if and only if it is a linear combination of the basis elements in degree 2, which is the case if and only if this matrix equation has a solution. So we look at we solve the equation. If it has a solution, X is in. If not, it's out. So here, what do you think? It's out. So this is out. So, but what would actually be in the homology language? So the homology language, I try to point out, has to do with independence. So what can we say about independence in this system? Well, the processes are the philosophers. A given philosopher is certainly not independent from a neighbor at the table, because these philosophers have to share jobs. They cannot proceed independently from each other. But a given philosopher would be independent from any philosopher who is not a neighbor at the table, because these two philosophers can proceed simultaneously without any problem. And so this independent structure should be reflected at the level of the homology language. Okay, and if you remember the theorem I showed about independence and the homology language, then the independence of, say, philosopher 0 and a philosopher who's not a neighbor at the table. So philosopher 1 would be neighbor, but philosopher 2 would not be a neighbor. So the independence of philosopher 0 and philosopher 2 would be represented in the homology language by an exterior product of an element coming from philosopher 0 and an element representing philosopher 2. And we have already seen that an element corresponding to philosopher 0 is the sum of the actions of philosopher 0. And since this is a basis element of the homology language in degree 1, we can get this element like this, HL1 index 0, instead of writing down the whole sum. And the product representing the independence of philosopher 0 and 2 would be then HL0 times HL1, 2. And which is this sum of products. Okay, and so now we expect that this is in the homology language, so that the matrix equation has a solution. So we can check that. And it gets a solution, so this is indeed in the homology language. Now, if you change, for example, the element like HL10, I put 1, what will happen? This would be an element representing the independence of philosophers 1 and 2. But philosophers 1 and 2 are neighbors at the table, they are not independent. So we expect that there's no solution. And there's no solution. Okay, and now, if I change again, like philosopher 2 now is philosopher 3, what will happen? Now they are not neighbors at the table. This element should be in the homology language, that should be the solution. And again, if I change in 4, philosophers 1 and philosopher 4 are independent, they are not neighbors. And so we have a solution. And you see how this works. I hope that this discussion here illustrates that understanding the homology language and understanding independence are quite related, and that in order to reason about things like this, such a program in Sage can be helpful. Just to terminate, the HDA here for the philosopher system is of dimension 5. So there can be homology language in degree 3, 4, and 5. What about homology language in degree 3? What do you think? Well, if you think in terms of independence, 3 philosophers, necessarily 2 will be neighbors at the table. So these 3 will not be independent. So we expect there's no homology. And indeed, the program says there is not. It is defined. Now, in reality, it's obviously zero. Okay, so thank you very much.
So questions? Yes.
Thanks, very interesting. So just a first comment, I think probably at some point, I mean, I'm happy you have also some implementation that we have some information with some element and some stuff. Maybe we should exchange it a little bit to, I mean, successful communities, they have, libraries that we share and stuff. Probably we should talk again back into trying to implement things like that. But apart from that, so for what positions of the
it can actually be in any kind of proficiency, but here it's implemented with these
proficiency, yes. But then you have some interest to have, I mean, you could consider ZP or then Z for the package, and not just finite fields, right? You would consider.
Here it works like this.
Yeah.
The homology computation is done with chomp.
Yes, and chomp.
And chomp, it's a very good
Yes,
implementation first, chomp, because it computes homology, and you can have generators.
Yes.
And this computes the labels in homology without any extra action. And chomp works with coefficients Z and finite fields and things like this. Since I call this, if I want to call this, I need to give the input for chomp. And doing it with other stuff like Z2 coefficients would be to have the patience to write the signs in the differential of the chain complex with as signs. And here I only put
That's would be have an interest if you had looking in constructs, I guess. Maybe some rather complicated elements with coefficients that you need to consider, and not just.
no, because since the homology language is a submodule of the exterior algebra, torsion elements will always have 0.
Yes.
So they don't are not 0.
Other question. Probably the answer is yes. You can also compute the ranks of the homology groups and get some generators out.
Yes, chomp. Yes, chomp computes the homology
In terms of
ranks, and but it computes also the generators. So those that have label 0, which are not seen here, I don't look at label 0 or just 1. Right? They are listed there.
Let me jump in with a question. So in the computations you showed us in the end, which were very impressive, by the way, all your solutions ended up having 1, 1, and 0s everywhere else.
Yeah, that is because it's a monomial. If you would take the sum of HL0 times HL2 plus the other guy,
yes, okay. Okay, so you have only 5 monomials because you had only, I mean, there were 5 coefficients, right?
Yeah. And what are they? It's the independence is generated in degree 2 by the pairs of philosophers who are independent.
Yes, exactly.
0, 2, 0, 3, 0, 2, 0, 3, 0, 4.
Yeah.
1, 3, 3, 1, 4, No, there's 6.
There should be 6, right? I only saw 5. Yeah. This is precisely my question.
No.
No, 0,4 is not even.
0,4 is not. Okay.
Yeah, so this we missed this one. So there are already 5. Yeah, okay, very good. I have another question. Just stop me if you can. Georg, Krzysztof and I, we were looking at each other when you mentioned the problem that if you have a transition system and you want to fill in independent squares, you have 2 ways of doing it and you don't know which one. And because this is something we were discussing for months already also, right? This is why Krzysztof has this event order in his item sets. Sorry?
To pick one.
Yeah, exactly, because you have to pick one. But of course, if you don't have any higher dimensional squares, you cannot easily pick one. Right? It's a problem which bites itself in the tail.
To order your levels.
Yeah, exactly. Yes, yeah. Which is precisely the solution that Thomas was proposing, right? Only it's a relation on the letters, and not necessarily an order. That's very interesting, and I think we should talk more about this. I'm looking at you guys for other questions.
Yeah. So this, before you were talking about this, instead of taking this symmetric relation or the reflexive relation, you can just take a non-looping relation, right? And then the homology language will not see the difference.
Yeah.
And then you can generate the bigger one, and you'll have all the information that you wanted, but it suffices just to have the smaller one, right?
Yeah.
Just this one relation, which seems to say then that the direction doesn't, I mean, which choice you make doesn't really matter.
Doesn't matter.
As long as to homology, right? Which sort of, it would be nice to talk about if this has anything to do with higher dimensional rewriting and filling in. That's what it made me think.
Yeah, just a little comment about that. A priori, I would have thought that it doesn't matter at all whether you fill it in twice or not, because I look at the squares and high dimensional cubes as an information that the actions on the border can be executed simultaneously at any part. And so if I give this information redundantly many times, it doesn't matter, it's the same information. But that's not true, because if you think of the boundary of a 3 cube, and you fill in everything right like in the boundary of the 3 cube, and then take off the square on the top, and you switch the order, then you won't be able to fill in this anymore. And therefore, because there's no 3 cube whose faces are compliant with that. And so the choice matters, but it doesn't deal what is for the homology language the case. It doesn't matter as long as you choose a cyclic relation that that has a symmetric closure as independent.
It's a question of consistency, right?
Yeah. So because this generates on a cube a strict order of the edges.
And all comes from the problem that what we would really like to look at is symmetric HDAs, because we don't want to care about those things, but then things get too big and we can't handle them anymore, right? So you have to choose some kind of order so that you can work directly in the pre-cubical category, not in the symmetric cubical category, and you have to do it consistently. This was not a question. I have another question. I don't know if it's a good question. So you call this the homology language. Why not just the homology? What does it have to do with languages?
Oh, the homology is something else.
Yeah.
It's the image of a labeling.
Yeah.
So therefore it's a language.
But does it give you back the notion of the standard language of an automaton?
No, but it's analogous. It's if you have the language of an automaton is the image of the labeling function for certain complete paths.
Yeah.
Here, the homology language is the image of a algebraic labeling function.
Yeah. Okay.
It's therefore it's just this.
Okay. So it does make sense. Okay. So I have run out of questions, and it seems that you guys also. So let's thank Thomas once more. So now starts the interesting part of the demo, right? Because